To get power, you have to multiply the voltage by the current. In this graph, 120 volts RMS voltage is represented by the red waveform. 3 amps RMS current is represented by the green waveform. They are multiplied together to get the blue waveform, which represents power. An interesting thing to note is that the frequency of the power waveform is double that of the voltage or the amps waveform. To be honest, I have no idea why this is the case or what the implications are, but I've just thought it might be an interesting thing to just note. Okay, let's see what the average value is. Right, 360. That's right, because it's 120 multiplied by 360. Right. So what do I mean about direction? Well, when power is coming into your house from the grid, it's travelling in one direction. Then, for example, if you have solar panels exporting power to the grid, it's going in the opposite direction. So I can tell which way it's going. It turns out when power reverses direction, the phase of the current changes by 180 degrees. So I can simulate this in my program. So there we go. 180 radians for current. Yep. Okay. So let's see what happens when we do this. Right. Okay. Right. The waveform for the current is now 180 degrees out of phase with the waveform for the voltage. Right. Okay, you'll notice that the waveform for the power is now below the 0 axis. So any value calculated for this waveform is going to be minus. So let's see what that value is. Right. Minus 360. Well, that's correct because it's still 120 volts RMS, still 3 amps RMS, but now the direction has changed, so it's now negative. So I'll just walk you through a little bit of the program to show you how it works. Okay, this is initializes some variables. Total of samples. This is going to be the variable that I use to hold the total values of all the values for power. So there's going to be 256 of those, and so you add them all together and then divide by 256 to get the average. Okay, RMS voltage we initialized to 120, RMS current we initialized to 3. Now when you're using a sine function, it returns value between -1 and 1. So what we need is the peak voltage, so that when it hits 1, it's 1 times peak voltage. So that's the peak, and when it's low, it's -1 times peak voltage. So that's the trough. Okay, so we need to do this for both current and voltage. So to do this, you just multiply the RMS voltage by the square root of 2, and that gives you the peak voltage. Okay, Watt scale. Right, when I plot the waves, the waveform for the power was too big to fit on the screen, so basically I've had to scale it. I've had to reduce it by, well, the half. Okay, so that's just to scale the waveform down. Amp scale, well, the amps are tiny, so I've had to scale those up to make it look like a nice sine wave. This is just for plotting, it's not for working out power. Okay, number of samples, as I've already said, 256. Right, this is just defines the draw axis procedure, and this just executes it. It just draws the x and the y axis. Right, this just starts a loop for counting range number of samples. That just for counting range 256. It just starts at 0 and goes up to the value of the number of samples -1, so that'll go to 0 to 255. Okay, then I work out the angle at this for this particular value of count. So just multiply by 360 divided by number of samples, because we only want 360 degrees, because we only want one sine wave. Right, the sine function in Python only takes radians as an argument, so I've had to convert the angle to radians. So that's what I've done here. And the reason I've done it for both voltage and current is because I wanted to change the phase of the current to by 180 degrees in order to change the direction of power. Okay, so I'll simulate the reversal of direction of power. Okay, so next, this works out the values for the y-axis of the waveform. So volts equals sine of radians for voltage multiplied by peak voltage, as I've already explained, and amps does the same thing for amps. Watts is amps times volts. That works out the values for the power sine waveform. Okay, total of samples. So as I've said, I initialize that to 0, and each time it goes through the loop, it adds another value of what's onto what were previously there. So that it'll add 256 values of watts together, and then at the end I can divide by 256 to get the average. Okay, plot. So this just plots the for any value of count. It plots the dots of the waveforms. So this plots the voltage watts, voltage dots. Okay, for angle at sample multiplied by 3. It's just I've multiplied by 3 in order to make it a longer sine wave, so that it's not all crunched up. But the value of the volts is fine. Okay, current, same thing for the x-axis. For the y-axis, I've actually scaled the amps up by 5. So amps times amp scale. That's in green. For the power, I've same thing for x-axis, but for the y-axis, I've multiplied by the watt scale, which divides it by 2, so it allows it to fit on the graph. Okay, Pygame display flip. Every time you draw something in Pygame, you have to flip the screen in order to display it, so that's what that is. So every time it goes through, it flips it. Okay, and when it's done that 256 times, it waits for a key to be pressed, and then it prints the total of samples. So that's all these samples added together, divided by the number of samples, in order to give you a value for watts. So I hope you've enjoyed it and understood it, and I'm sorry if you haven't, but thank you for watching. So see you next time.